similar experience.
Yeah, 1 parsec. I don't think so because I don't know back.
Okay. Yeah. It's cool. Yeah. HWO really needs to happen because it really seems like it solves a lot of our problems. How did it go, Chris? Good?
It's more I now know that this photo is
Very interesting. I mean, basically, the cycle is it's hard to appreciate
We're still waiting on one of our 3 groups.
Yeah, last week. Well, it was a big range, and as we've been seeing, like 16. Yeah. Well, I mean, we keep coming back to each tree.
Yeah, we're massive.
Seeing all this. So,
They're coming for it.
It's all in the center.
They're just in rapture about spiral arms. They're coming.
At that point, I have like fighting.
Did they like? Did they figure it out in a half an hour? Do they have a number? Ask Bob Ben.
Yeah.
Honestly, how many?
Don't ask.
No, galaxies.
yes, probably.
4 minutes. Took advantage.
Smile.
How?
So, yeah, he said he had 0.5%. But I'm wondering if that's
Like a comment from the referee, but it was absolutely, it was like,
so Muse just opened
so they were like, oh, what's like this?
like a material.
You're never remnant size.
So whatever was possible.
You're right. The worst thing is
Yeah, so I would really, I've got a sample.
oh yeah.
Right.
First you
I don't think it'll be.
throw that in the Slack.
These are the computations I have yet to do. I need to see.
Should I go? Cool.
Like I said, if I can get.
All right, guys, let's do our summaries from our group discussions. There we go. Okay, so I hope everybody had fruitful discussions. The discussion in here was good, so I hope all 3 had similar discussions. So let's do our summaries here. So whoever was going to report, Chris, for the discussion all about dust. You have about 5 minutes.
5 minutes. Okay.
this was partly just the premise of my desire to interrogate Clark after his talk in order to learn where there's hope and where there's not hope for people who care about dust. And he was very, very amenable in that. So everything is degenerate with everything else was probably the main takeaway of the dust people. But to kind of whistle stop tour through our notes is that the fact that dust grains can, in a dense molecular phase, most of their mass can then be the accreted material versus the seed material, means that they can very quickly lose their signature of their formation site. That said, we're not sure what the signatures of formation site especially are, or how distinct they would be. Like Makako sees, crystalline stuff in the planetary nebulae. We see crystalline stuff in the toruses, tori of AGN, but we don't know what fraction of the stuff being formed there is crystalline in the first place, and therefore it's very hard to imagine even using crystalline dust as a tracer of where stuff came from in the general ISM. We of course have these pre-solar grains we retrieve from meteorites. But the issue is that the process of identifying what is a pre-solar grain kind of is dictating what we identify as that pre-solar dust, and then it goes on to get melted in solution in the lab. And so it's, again, very hard to tease out what might be a heavily processed grain from a different environment. What else do we have here? The environments where grains can grow can be still quite warm and reasonably diffuse ISM, maybe a factor of 10 or so difference between the different environments, which means that what we'd really like and what Clark will hopefully produce is basically observational tracers saying how much faster the grain growth rate is expected to be based upon mainly the density and the temperature. And if we have like observational fingerprints of these, we can, hopefully in the not immeasurably distant future, have grain growth rate maps of nearby galaxies given the environment we see there, which would be utterly delightful. Although a lot of problems fall back to the fact that some of the sort of very basic work that things are still based upon back in the day use very coarse binning for things like grain size distribution and the like, which is something we're still kind of suffering from the after effects of today. We then kind of bounced around to are supernovas net producers or destroyers? And we were reminded the fact that there are models which show that some of the dust ejecta can even be in front of parts of the forward shock, which that should then definitely survive. And the question of what can survive the reverse shock is very dependent upon the geometry and the density, but because there's all this turbulent mixing in there, it's very hard to track. And then we also brought things round to the implications of the supernova light echoes, where of course you had these very sharp, like Josh can correct me here, but like up to order of magnitude or more very small density enhancements on very small scales in the ISM. And so even if you're in low density ISM, a given dust grain could be dipping into this factor of 10, 50 or more denser ISM on fairly regular intervals. And because the dust grain growth goes with the density squared, a situation where a grain in very low density ISM could go through enough spurts of, short, sharp grain growth in these environments that where we think grain growth might happen might be on higher resolutions than we can ever hope to probe. So that is, I think, the whistle-stop tour of what we discussed. And we basically had an idea of where we can reasonably hope to learn more things and where we maybe can't, I think was the general takeaway. So I will leave it there. And thank you, everyone who contributed. I learned a lot. Thank you.
Okay, Becca, you want to give our summary for number 2, which I think was more questions than answers.
Yeah, so the question that we were thinking about was, what physical resolution do you need to get the ISM right enough? And how does that depend on the question that you're asking? And we had a great discussion, I think, about the variety of contexts and what sort of resolutions might be relevant there. It sounds like, drawing a broad brush, that 1 to 10 parsec resolution might be a sweet spot for a lot of things. That's not going to solve everything, certainly. And that, this is possibly expensive to do observationally, but not impossible. Some of this data exists already. And, it would be worth, I think, pushing. I think we came to the conclusion that it's worth to get down to those scales. We had a discussion about, at what point do you need sub parsec resolution to get things in really dense environments right? And at what scale, if you degrade resolution, does that start to break down? So thinking about doing resolution studies in places like the local group and the Milky Way and the Magellanic Clouds, where we have, in my view, as an extragalactic person, infinite resolution, to do these resolution studies to see where these trends, either with, star formation rate tracers or dust extinction corrections or star cluster properties, H2 region properties, feedback measurements, at what scales do those measurements start to become wrong above some threshold that you're comfortable or uncomfortable with? And this seems like something that's worth doing, and that we have the data in a variety of environments to do these kinds of tests, and that would be a really useful exercise. We also noted that for simulations, simulators have a similar issue, right? They also don't have infinite resolution. And they are, used to doing these kinds of resolution tests routinely. And so having their, resolution be informed by what the observations needs and vice versa would be a really useful thing to sort of come together on, so we can make the most use out of each other's very expensive observations or simulations. There was also a little bit of a point made about, can we, in addition to doing these resolution tests, can we leverage the higher resolution data to in some way correct things when we have lower resolution? Is there some way we can make it not quite as wrong using what we know from higher resolution data? There was also, we noted that what resolution you need is highly dependent on what timescales you care about. So if you're okay averaging over, 100 million years, then maybe, looking at things in super fine detail isn't necessarily as important. And the same thing if you're thinking about statistics versus a case study. Those two things are, might mean that you have different physical resolution needs to get it, again, right for whatever your science case is. And then finally, we had at the very end, we had a little bit of discussion about, is asking for 0.1 parsecs crazy or infeasible? And if we wanted to, make a concerted effort to try to get this sub parsec resolution in other galaxies, where would we want to spend the time and effort to do that? Would we want to zoom in on these really dense, very extreme star forming environments? Is doing that going to bias us in some way that would be very not helpful? It would be useful to additionally have, simple regions that the simulators can compare and benchmark against. Or, do we want to have a couple of these more diffuse regions? Are we really missing something important by not having the high resolution, detailed physical insight in the regions that aren't massive and crazy and representative, or not representative, but where we tend to focus our efforts? So yeah, not a whole lot of answers, lots of questions, but I think we have I thought we had some good inroads into ways to make progress on starting to address this question.
Okay, and last but not least, does the Milky Way?
I volunteered.
Okay.
Since I have less of a stake in this, we thought that I thought it'd be good if I give my unbiased view on this. So essentially, the question was, does the Milky Way have spiral arms or not? And we started this off with, why do we care whether the Milky Way has spiral arms? And we came up with 3 answers. The first answer is I thought was quite beautiful, which is to know our place in the universe, to understand how we compare to other galaxies. and I really liked that. That was one of the reasons. It's just a better understanding of where we are and where we came from. The second reason was so that when we simulate galaxies and we simulate these arms, is that correct? Like, we don't want to be simulating arms if we're trying to mimic the Milky Way, if the Milky Way doesn't have those arms. And the third reason that we want to understand if the Milky Way has arms is it informs us about how gas is organized into structures to form stars and star-forming regions. So all these three reasons together led us to why we wanted to have this discussion. Then we voted. We voted on, does the Milky Way, is it a flocculant? Is it a grand spiral? So your beautiful, perfect, beautifully collected arms? Or is it something in between? So it has like segments of arms. It's not quite flocculant. It's not quite grand design. And we decided at the end of the discussion session, we would revote. So grand design, we voted 0. Not a single person believes we're a grand design. When it came to flocculant, 4 people voted flocculant, and then 16 people voted for this in-between multi. We then went into basically went into the discussion of spiral arms are a lie, and that was mainly led by Josh, was it? Yeah, because it's a lie because the LV diagram is just we can't really see spiral structure. We just make it up with the LV diagram, and then we spent the next 15 minutes just basically saying the LV diagram is a lie, which I thought was quite nice, and it was quite fun. And then we ended up, going into some of the history of where spiral structure came from, why we care, and it basically came from this 1950s of just looking at OB associations and seeing that they're a little bit, you have like these arcs, and therefore we have spiral structure. And then we finished this without any major conclusions. We just ended up revoting after saying that spiral structure is a lie based off the LV diagram. We revoted on what do we have spiral structure. The votes remained basically the same. One person changed from flocculant to multi-arm, and one person said they're half dipping between the flocculant and the multi-arm. So it basically went from 16 to 4 to 16.5 to 3.5. So I hope that answers. I hope you've got a good overview of what we discussed, and I think this is a really interesting topic to do. And I think I'm going to give my opinion. What I want to see now is people who do sims create these beautiful galaxies and make the LV diagrams, have the flocculants, the grand designs, all of these things, make the LV diagrams, and then draw it yourself. And how correct are they? That's what I want to see. Anyway, thank you.
Thank you. All right, thanks everyone for another great day of discussion section.
Yeah, we're gonna erase the board, put the old ones that weren't discussed, get your options to put some new ones. So continue to vote and get some more new ideas. But for right now, we're gonna do our poster session.
Yeah, so if the Flash Talk people can come up.
Yeah. Oops.
I think we'll start with Tom. We got 1 minute.
You're better at this than I am. Take it away.
There you go.
All right. Well, my poster is on 2 programs with the JWST to observe accretion-driven feedback around nearby protostars. The first program investigating protostellar accretion, we did 5 objects that span the mass spectrum with the IFUs with NIRSpec and MIRI. And so you can see one of the spectra that we have of one of our sources, which are just incredibly rich. And in particular, we can separate out different components like very high velocity jets and low velocity winds, all driven from the disk. And we think the low velocity winds are actually the more dominant and important component because they have, when they're lower velocity, they have bigger mass flow. And then the second part is we have a second program, a large program where we did NIRCam, NIRSpec, and MIRI observations of the OMC23 region just north of the Orion Nebula. And what we're going to present here is actually this beautiful mosaic Rob Gudermuth put up, which is the first sort of public release of this incredible mosaic along this filament showing all of the feedback from the protostars onto the surrounding clouds. So come by.
Thank you, Tom. Next, we'll hear from Barry. Wrong one. Wrong one? What? You got too many windows open. How's that? Okay, here we go.
Good afternoon. So as Dries mentioned earlier this morning, the PDRs for all collaboration has targeted the prototypical PDR, the Orion bar, for observations by JWST. And this has enabled studies of a large variety of, might add, very beautiful aromatic infrared bands. So in this study, the 10 to 15 micron ALBs in particular have revealed the nature of the molecular edge structures of PAHs in the bar. They are compact and symmetric with plenty of solo and trio hydrogens on the edges, and the edges are eroded toward the PDR surface. That is not all that meets the eye. We find evidence of another class of carbonaceous AIB carriers. They're more mysterious and shy. These are the very small grains, and they're hidden and shielded in the molecular zone of the PDR. This work is presented in post number 8. That's at the very end on the wall on the right. Thank you.
All right, next we'll be hearing from Divakara.
Hi, I'm Divakara Maya from Mexico. So this study is about NGC 628, and it's basically using the TRGBs for obtaining the metallicity gradients in galaxies. The TRGBs are most well known as distance indicator when they are observed basically in around 9,000 angstroms and either 814W in HST or 090W with JWST. However, I mean, in infrared, in the JWST bands, the TRGBs are not used as distance indicator basically because their magnitudes and colors are metallicity dependent. So what we did here is to use this metallicity dependence to obtain the metallicity gradients or metallicities in different parts of this galaxy. So what we did is to divide the entire image into 90 regions of roughly 1 kiloparsec square area. And in each of the regions, we could get CMDs of the resolved stellar populations and get the TRGB for each one of these points. No? So the plot, which is not well focused, and the left, so we show all the TRGB points. So they are not in the single point. They're distributed basically because they have different metallicities or different extinction. And one good point about these JWST filters in this filter combination is that the dependence of metallicity and extinction are orthogonal. So we can clearly distinguish which is the metallicity effect and which is the extinction effect. Finally, using this, we have then the right plots, the metallicity gradient, which is the metallicity of the oldest stars in the disk. So we are seeing the metallicity when the disk was just forming. We compare it with the gas phase metallicity, which as expected is much above, 1 order of magnitude above. So this gives a new tool to find stellar metallicity of the oldest population. Thank you.
Next, we'll hear from Leo.
So, hi everybody, my name is Leo. I'm a first year PhD student at Sgr A Paris-Saclay. So my team and I got interested in the efficiency of the photoelectric heating. So with the new SOFIA C+ map and some SCD modeling with the TEMIS model implemented in a hierarchical Bayesian code, we linked the photoelectric heating efficiency to the local dust properties. we also managed to do a phase decomposition of the observed C+ luminosity using some ancillary data. And we did that in order to not get contaminated in our estimation by some other heating mechanism. So if you want to know more about it, I'll be glad to talk with you about it. Thanks.
And lastly, we have Adam. There you go.
Excellent. Thanks, Steve. Okay, so M33 has been studied to death. Sumit was just showing us some lovely stuff from his talk earlier. But we have some new JWST imaging of the center of this very well-studied face-on local galaxy. And I think it's one of the most detailed pictures we've ever obtained of the center of a galaxy. So you can see our imaging here. We have resolved in very fine detail star-forming regions. You can see NGC 595 looks a whole lot like the Orion bar PDR that Barry was just showing. And we've resolved stars and dust at incredibly high resolution. The nuclear star cluster is resolved into stars for the first time. And we have 10 filter combining with Hubble Space Telescope imaging. We've got 10 filters photometry for millions of stars. You can see all of these color magnitude diagrams down on the right there. And the main result, science result here that's brand new is that for the first time ever, we have reconstructed the star formation history in the central 200 parsecs of M33. And it shows this very significant enhancement about 1 or 2 billion years ago that we think tells us something about the interaction history of M33. Thanks.
Cool. Any announcements? All right, no announcements, so we'll be back here at 4.